В общем, когда можно будет начинать, пожалуйста, скажите. Так, сейчас.
Сейчас, а можете что-нибудь сказать?
Проверка связи.
Саша, как там?
Да, все прекрасно слышно. Соединять громко, тебя слышно тихо, как это должно быть. Отлично, все четко.
Центр дана, можно начинать.
Так, значит, можно начинать. Хорошо. Так, значит, давайте. Well, let's briefly recall what we saw last hour. So we saw this mysterious formula. Let me write it like this. Yes. Well, later on we'll write this. We'll write the same thing as simply MON of X. Yes. Yes. Thank you. Well, so this is the. This is the.
Нет, справа.
We'll briefly see where this all comes from. This is the Pontryagin-Thom theorem, and our goal for the next hour or so is to see the proof. By the way, sometimes it's called the Thom theorem. But the construction used in the proof is called the Pontryagin-Thom construction. Now, before we prove this, we need to decipher the formula. So we need to basically we need to understand what MO means. Now, to do that, we first need to recall classifying spaces and the classification of vector bundles. So I'll recall a general construction of the classifying space for an arbitrary topological group. We'll need this later, but after that I'll give an explicit construction for linear groups, which means a closed subgroup of GL GL something of R. So we start with an arbitrary topological group, and we construct we start with the space EG, which is a sufficiently nice space, well, I suppose Hausdorff and well, let's say Hausdorff with the right free action. Of G such that the projection to the quotient space is the projection of a locally trivial vector bundle. Locally trivial bundle. Sorry, not a vector bundle. So Vg is the classifying space of G. Now we will mainly be interested in the case when G is let's say a GLK of R.
But I think we need to say that G is homotypically trivial.
Oh yeah, yes, thank you, locally trivial vector bundle, and thanks, EG is contractible. So let's give an explicit construction when G is GLN or GLK, or when G is a closed subgroup of GLK. Such as O of K, SO of K, or U of half K, or SU of half K, or SP of K by 4, and so on. Now, in this case, we can simply take EG to be the space of k-frames, which means k-tuples of elements which are linearly independent. In R infinity, which by definition is the direct limit of finite dimensional RLs with the direct product, with the direct limit topology. meaning the subset is closed if and only if its intersection with any finite RL is closed.
Для G равно уже LK.
Что? Еще раз?
Это равенство для G равно не подгруппы, а для просто G равно уже LK.
Ну, если у нас есть действие группы, то у нас есть действие подгруппы тоже.
То есть оно одинаковое.
Well, the thing is, this group acts on this space. The space is contractible. There are there are several ways to prove this, including constructing an explicit contracting homotopy by hand. Or another option would be to represent this as the direct limit of finite dimensional Stiefel manifolds, and then basically one can observe that the homotopy groups of a finite dimensional Stiefel manifold start in a very high dimension, provided L is sufficiently large. Does this make any sense? If not, please let me know. And that includes people who are with us on Zoom or elsewhere. Anyhow, so we have a contractible space with a free action of GLK, meaning with a free action of any subgroup of GLK. Now, well, the map from this space to the quotient is the projection of a locally trivial bundle, and again, this is something that can be checked by hand, and this space is the Grassmannian of K-planes in R infinity. As people often denote this space, GK of R infinity. Now, why is BG called the classifying space? Well, it classifies. But what does it classify? Well, for general G, it classifies principal G bundles. But for G equal GLK, there is a simpler description, namely we have a linear group, so instead of principal bundles, we may as well consider vector bundles. So let's focus on vector bundles. I'm not allowed to use this board, am I? Well, anyhow, let's. Well, there's enough. There is enough.
Там пишет о том, что все доски видно. Там есть. Правая видна, но не все.
Так, ну давайте дождемся Семена и посмотрим.
Пожалуйста, ваша смотрю надписи доска, мелкая доска, это как зрение.
Ну, хорошо. Значит,
Автор этих надписей я полное разрешение не стереть.
Okay, so let's see in which sense BG classifies classifies vector bundles. But before, just an obvious remark. Instead of all frames, we may as well introduce the standard scalar product on R infinity, and then consider orthogonal frames and take this as EOK. Now this space EOK will be homotype equivalent to EGL, meaning contractible, and the question will be the same. So we will not distinguish between BGLK and BOK in the sequel. And by the way, if we have a group homomorphism which is a homotype equivalence on the level of the B's, we also have a homotype equivalence. So this is well, it's not a coincidence. Now, BGLK classifies rank K vector bundles. Now, before I explain this, there is a tautological vector bundle on VGLK of R. Now, is everyone familiar with this bundle, or should I recall the definition?
все камерные подпространства.
Значит, знаете ли вы, что такое тавтологическое расслоение на Гроссманиане? На Гроссманиане камерных подпространств в R бесконечности. И если это вызывает хоть малейшие вопросы, то давайте проговорим.
Я думаю, вызывает.
Хорошо. Well, let's review this. It's important.
Можно еще вопрос? Там вот EG, вот A-frames имеется в виду типа K-векторов линейно независимых.
Наборы из K-векторов, которые наборы являются линейно независимыми.
И с точностью до порядка.
Значит, фрейм упорядоченный. Значит, базисы не упорядочены, базис это подмножество, фрейм упорядоченный.
В определении ЕЖ, которое вы только что стерли, там было написано, что хорошее пространство со свободным действием G. Действие тоже что-то требуется?
Значит, действие требуется, значит, чтобы отображение фактора по этому действию было бы проекцией локально-тривиального расслоения. Значит, это тоже только что было на доске, но только что было стерто.
Все, да?
Да. Ну, из этого мы, в частности, получаем, что и фактор тоже Хаусдорфов, значит, поскольку значит, локально эта штука устроена как произведение чего-то на группу. Well, let's review this construction, the tautological bundle. Ну, естественно, должно быть непрерывно, но, значит, Игорь. Okay, let's review this construction. The total space of gamma n is gamma k is the set of all couples v comma x inside gk of r infinity cross r infinity. Such that x is in V. Does this make sense? Well, a straightforward argument shows that this is a vector bundle over gk of r infinity. And this is the, in a sense, the most important bundle, because every other bundle is obtained from this one. More precisely. Every vector bundle over X is isomorphic to the pullback of gamma k under some continuous map from X to gk, gk of R infinity. And second of all, two pullbacks are isomorphic. In other words, f upper star of gk is isomorphic to g upper star of gamma k. Sorry, it's gamma k. If and only if f is homotopic to g, where f and g are maps from X to gk of R infinity. Does this make any sense? So this is the sense in which the Grassmannian manifold BGLK, or which is the same GK of R infinity, classifies vector bundles. As I said, for general groups, there is a version of this which says that the classifying space BG classifies principal bundles. We'll talk about this later. Are there any questions? Now we need the Thom spaces. Now again, this is something which many of you have seen, but maybe not everyone. So shall we? Yeah, we shall. Okay. Thom spaces. Thom spaces of what? So suppose we have a real vector bundle. With a metric. Now, let's call this bundle psi. Does everyone understand what I mean by a metric? If not, please let me know. Now, starting from a real vector bundle with a metric, we construct the bundle of unit vectors, of vectors of length 1, and the bundle of unit disks, meaning the space of vectors of length less than or equal 1. The Thom space. The Tom space is just a quotient of the bundle of unit vectors, of the bundle of unit spheres by the bundle, no, sorry, of the bundle of unit disks by the bundle of unit spheres. And up to homotopy equivalence, this space does not depend on the metric. Семен, можно ли писать вот на той доске?
На той доске можно писать, да, все 4.
Все 4, окей. So, H. So th of psi does not depend on the metric up to homotopy equivalence. Now, the Tom isomorphism theorem. Sorry, no, I need to put a tilde here. Sorry, the Tom isomorphism theorem the Tom isomorphism theorem says the following thing: the reduced homology of the Tom space is the same. The reduced cohomology of the Tom space is the same as the non-reduced cohomology of X, all cohomology with coefficients mod 2, with a shift. Now, the isomorphism is given by the coproduct with the Tom class. We won't need this right now, so I will say no more about this theorem. But still, does everyone understand what it says here?
Какая-то рамка расслоения?
Yes. K is the rank of the bundle.
А что вы спросили последнее?
Что?
Что вы спросили?
Все ли понимают, что здесь написано?
Понимаю, в смысле.
Ну, иногда бывает, что там написаны какие-то буквы, что они означают неизвестно. Вот это хотелось бы избежать. Формировку, да. So very briefly, the map, the isomorphism is given by copying with the Tom class. The Tom class lives in the kth homology of the disk bundle by the sphere bundle. By the way, there is a very detailed proof of the Tom isomorphism theorem in the book called Characteristic Classes by Miller and Stashev. Well, so now we know what the Tom space is. Now let's see how the Tom spaces behave when I take a bundle E and add a trivial bundle. I will denote the trivial bundle epsilon k of x, where k is the rank. Now, and when it is clear or irrelevant which x I take, I will drop the x. Now, there is a formula which we'll use many times in the sequel. The Tom space of psi plus epsilon k is the kth suspension of the Tom space of psi, which is again a formula that many of you will have seen. But let's see where this formula comes from. How to prove this formula? Well, there is another formula, which is easier to prove. And which says that the Tom space of the direct of the Cartesian product bundle is the same as the wedge of the smash of the Tom spaces of the bundles. Now let's see if any of this makes sense. Well, this is something we already know, and so is this. Well, if suspension is mysterious, please let me know. Now, what is this? Well, suppose I have psi and eta two vector bundles, one over a CW complex X, the other over a CW complex Y, I can take the direct product of the total spaces, and it will be a vector bundle over the direct product of the bases, and this vector bundle is called the Cartesian or direct product of psi and eta. Does this make any sense? Now, by inspection, there is a homotype equivalence on the level of Thom spaces, which says that the Thom space of the direct product is the same as the Thom space of has the wedge. The smash of the Thom spaces. Okay, does the smash make any sense? If there are people who don't know what smash is, please let me know. By the way, we already had it here. Well, now, using this formula and the fact that the direct sum of psi and the trivial bundle of rank k is the same as the direct product of psi and the trivial bundle of rank k over a point.
Подождите, мы сейчас из второй формулы первого?
Да, мы хотим вывести первую формулу из второй. Ну, потому что вторая, она такая более понятная, а первую мы будем использовать.
А вторую мы будем?
Ну, вот вторая это упражнение, но ее как раз легко понять, ну, проще, чем первую.
У нас все с отличными точками или нет?
Нет. Значит, ну, здесь... Значит, нет, ну, в общем, чтобы брать смеши, нам, конечно, нужно отмеченную точку. Значит, но пространство Тома получается с хлопанием. Там автоматически возникает отмеченная точка. Well, a useful remark, the Thom space has has a base point. Why? Well, it's obtained by collapsing something, and every time we collapse something, we get a base point. Вопрос был в том, есть ли отмеченные точки.
Нет, ну это скорее вопрос про что такое надстройка пространства. Ну, здесь настройка с отмеченной.
Значит, что такое настройка? Да. What does this have to do with this? Well, the Thom space of RK to Vt is the same as dk by sk minus 1, which is the same as sk. Now, taking the wedge with sk, it's the same as taking the k-fold suspension of x. So using this formula, this fact, which is straightforward, and this fact, which is also straightforward, we deduce this formula. Does this make any sense? Okay, I've run out of water again, so I'll make a trip to the well. Good. Okay, so yes, we have this formula. Let's now see how it helps. I recall that I have the tautological bundle over gamma, the tautological bundle gamma k over the Grossmanian gk over infinity. Let me add one copy of the trivial bundle. By the classification theorem for bundles, I have a map from B from B GLK to B GLK plus 1. Why? Well, this is a rank this is a bundle of rank k plus 1 over gk, so it must give a map from this space to this space by the classification theorem. I have a map of the Thom spaces. And this space is the suspension of the Thom space of gamma k. And now we basically have the non-oriented Thom spectrum. What do we have? Let's look at what we have. We have a sequence of spaces which I denote MOK, which are the Thom spaces of gamma k, the tautological bundle. And then for every k, I have a map from MOK to MOK plus 1, from the suspension of MOK to MOK plus 1. In other words, I have a spectrum.
Происходит почему? Из классифицирующего поражения,
да? Значит, ну, сначала мы говорим, что вот это эквивалентно вот этому.
Да.
Вот ровно вот по тем причинам, которые мы только что видели. А такое отображение существует, потому что пространство атома функционально по расслоению. То есть, если одно расслоение послойно отображается в другое расслоение, то пространство атома первого расслоения отображается в пространстве атома второго расслоения. И единственным образом с точностью до гомотопии. Если эта фраза мистическая, то давайте ее расшифруем. Но если она не мистическая, так понятно, то давайте пойдем дальше. A fiber-wise map of vector bundles induces a map of the Thom spaces, which is unique up to homotopy. And if this is mysterious, let's look at it in more detail. Otherwise, let's move on. Okay, so we have the non-oriented Thom spectrum. Well, which is already something. We know this ingredient. And by the way, well, we sort of know what this means. No, I've erased the beginning of the formula. So let's let's reinstate the formula. So MO pi k plus n of okay. Now sorry. There's one thing missing. One thing is missing. And that's the limit. We take the limit of this. Now it's more or less clear what which limit I take. More precisely.
Обозначаем группу. А, да,
More precisely, suppose I have a map from S k plus n to k wedge x plus. Well, I suspend the map. And I get a map from Sn plus k plus 1 to the suspension of MOK wedge x plus. But then I have a map from this space to this space, and the smash is functorial, so I have a map from the smash to the smash. And this is the direct limit that I have to take in this formula. Well, we don't have a proof yet, but at least we understand what the formula says. Unless there are people who disagree. In which case, please let me know. Okay, now we have this this formula, and no, we have this formula, and we want to prove it.
Это же изоморфизм групп, да?
Это изоморфизм групп. Значит, что изоморфизм групп?
С исходным термином.
There's a group structure here, and a group structure here, and the group structures will be the same. Well, let's see. The idea is very simple. We construct maps in both directions, and then we will prove that both compositions are the identities. Which direction shall we go in first? Okay, from the limit, I've already started in the opposite. Well, obviously we'll do both. So suppose we have. Okay, suppose we have suppose we have a singular N manifold as defined in in the first half. Now. Well, this manifold can be embedded in, let me write S n plus k. It'll be more convenient. This manifold M can be embedded in S n plus k for some k. One can take k equal to n, but it's not important for us. Well, starting from this embedding, one can construct the normal bundle of the embedding. Does this make any sense? The normal bundle obviously depends on the embedding. If we take another embedding, the normal bundle will not necessarily be isomorphic to the one we started with, but that's not important. The stable class will be the same. Let me briefly explain why. So the normal bundle depends on the embedding, but the stable equivalence class doesn't. Now, does everyone understand what the stable equivalence class is?
So it means that we can add the trivial bundles.
Yes. Or more precisely, we say that two bundles are stable equivalent if and only if by adding copies of the trivial bundle to each, we get isomorphic bundles. And the number of copies needn't be the same. For example, it could happen that for the first bundle we need to take 3 copies, and for the other bundle we take 2. And as a basic example, the tangent bundle of a hypersurface in the Euclidean space is trivial. Why? Well, let's say the hypersurface is compact, because otherwise we can embed the Möbius strip in R3, and it'll not be orientable. Now for a compact hypersurface, there is a way to trivialize the normal bundle, the result is we take the tangent bundle, add the trivial normal bundle, and what we get? We get the tangent bundle of the Euclidean space, which is trivial. So, as a result, the tangent bundle of the 2 sphere, for example, or of the n sphere, is trivial. Why? Well, the n sphere is a hypersurface in Rn+1, and so on.
То есть, если подразумевается то, что вот это нормальное расслоение в сфере, оно зависит от вложения, зависит там от К, наверное, ну, стабильный класс, то есть при фиксированном К, как бы, мы это смотрим, да?
Значит, мы, когда мы стабилизируем, мы разрешаем К меняться. Значит, мы вложили многообразие в сферу с коразмерностью К. Ну, естественно, значит, если мы вложим в там, с коразмерностью другой, то мы получим расслоение просто другого ранга, оно не может быть изоморфным, значит, исходному. Но это не страшно, потому что стабильно все получившиеся расслоения будут эквивалентны.
Понятно, при разных.
Да, и, соответственно, значит, все при всех возможных К, они все будут эквивалентны.
При одном достаточно большом, просто нужно целикер.
Да, и, значит, достаточно взять любое вложение, если К больше, чем там, ну, в общем, если К достаточно большой. Почему? Давайте поймем. Why all these bundles are stable equivalent? Let's see. Well, first of all, the Euclidean space Rn+k is contractible. There's no question about that. So all maps from M into the Euclidean space are homotopic. But for k large enough, isotopy and homotopy are the same, and that's why all embeddings from M to Sn+k for k large enough are not only homotopic, they are isotopic. And after this, it's a matter of time to prove that isotopic maps induce isomorphic normal bundle. Isotopic embeddings induce isomorphic normal bundles.
I believe that this is some complicated statement, but if we just replace the S by Rn, and we can do that, then I think we can just take the homotopy as a map.
Yes, yes. Yes, it's the same, basically the same idea. Suppose we have Sn or Rn plus k, it doesn't make any difference. Suppose we have two embeddings in the sphere. Then, if k is large enough, we can always take a point which does not belong to the image of either embedding, and then do what you propose. So the key thing is for k approximately 2n plus 3 or whatever, isotopy and homotopy are the same, and it's true whichever manifold we take here. It's a statement It's a general position statement. Doesn't really depend on the topology of the target. Okay, I think we have to finish. Unfortunately, so at least we understand the statement of the theorem. We haven't.
Можно сказать, как отображение устроено.
Ну, как устроен, я не хочу сейчас комкость, и все равно в следующий раз придется повторять, потому что, в общем, для тех, кто это видит первый раз, наверное, если сейчас что-то быстро скажу, это будет как бессмыслица. Well, we have seen the statement of the theorem. Next time we'll see the proof. Are there any questions? Okay, well, then I suppose this is it. And I need to